It's time to begin our discussion of energy methods and momentum methods as we discuss rigid bodies. We're going to begin our discussion with energy methods, and we're going to start the energy methods simply with a discussion of kinetic energy. Now, we've already looked at kinetic energy in translation, and we know that's just 1/2 mv squared. We do want to consider the possibility that there might be more than one object. Instead of just a single object that's moving with some velocity v, there might be multiple objects connected in some way, or maybe not even connected in some way. But the idea is that the total energy of the system is going to be the sum of each of the individual kinetic energies. And so I here represents each of the individual bodies. If there's 10 bodies, I will be 1, 2, 3, 4, all the way up through 10. And so you'll add the mass times each of the velocities. And v sub I dot v sub I is simply v sub I squared. I can write it as a vector dot product. It doesn't really matter. It's the magnitude of the velocity squared. And then you just add all those together. Well, it's of interest to note that this will equal the mass times the velocity of the center of mass. So the total mass of the system, that would be all the masses added together, times the velocity of the center of mass squared. This will give us the same value. Okay, so let's take a look now at kinetic energy of rotation, because this is going to be a new term for us. And the way we want to start that is, let's say I have an axis of rotation located here at A. Then the kinetic energy of one portion of this solid body is going to be 1/2 mv squared for that solid body. So assume a piece of this larger solid body. This piece right here has a cubic volume, and it's going to have some mass. Now the distance from the axis of rotation is r sub I. And that's actually a vector quantity, a vector position from the axis of rotation A to where this object is at. And then the center of mass of this oddly shaped object is going to be located here at r center of mass. I use the symbol here of the circle with 2/4 of it darkened in. Oftentimes we'll just register that with a G for the center of gravity. Okay, to figure out then what is the kinetic energy of that mass m sub I, well, that's just going to be 1/2 that mass m sub I times its velocity squared, okay, or its speed. Doesn't really matter when it comes to kinetic energy. Speed is what counts because it's not a vector quantity. But the speed, r sub I, is going to equal the distance, r sub I here, times the angular velocity, the angular speed even, of our rotating object as it rotates around our axis of rotation at A. And so the linear velocity is just r omega. Alright, so if I square that out, I get m times r sub I squared times omega sub I squared. And then let's just take this value and put it in parentheses. That's what I've done right here. But mr squared is the moment of inertia of this little tiny mass right here. And so when I sum over all of the masses that make up my odd shape, so this moment of inertia is equal to the moment of inertia about the point A. So you'll have to use a parallel axis theorem as you're contemplating that value. Now, if the object is not rotating necessarily around a fixed axis A, if it's rotating around a moving axis, then what you really want to do is you want to take the moment of inertia about the center of gravity. So as I look at the kinetic energy of an object that's rolling or rotating and translating at the same time, the total kinetic energy is going to be 1/2 mv squared, and it's very important that velocity is the velocity of the center of mass, plus 1/2 I omega squared, and again, very important that the moment of inertia is the moment of inertia about the center of mass, oftentimes referred to as I sub g. If you do the parallel axis theorem about some other point, you're actually bringing this value into play. So either do the moment of inertia about the center of mass and the velocity of the center of mass in your kinetic energy, and that's what I recommend that you do. Or in some situations where you have a fixed axis of rotation that's not at the center of mass, then you can do 1/2 I about that axis of rotation omega squared, and the translational kinetic energy is actually built into the moment of inertia about this other axis. It's part of the parallel axis theorem. And the way we know that is the velocity about A is equal to r omega, where r is the distance from the center of mass to A. So this could be A with respect to G or G with respect to A. It doesn't matter, and the reason it doesn't matter is because I square it. And so that would be 1/2 m r of A with respect to G squared times omega squared plus 1/2 I about the center of mass, so I'll call that I sub G, about omega squared. But this is mr squared, where r again is the distance from A to the center of gravity. And when I did the parallel axis theorem, that is the md squared that you saw in the parallel axis theorem. So I can add I sub G here, and you'll see a 1/2 in both terms and an omega squared in both terms. This is the moment of inertia about A according to the parallel axis theorem. So either go center of mass in both cases, or if you have a fixed axis. If the axis is not fixed, I don't recommend using a moment of inertia anywhere but at the center of gravity. But if the axis is fixed and you want to go around that fixed axis, then you're fine to use 1/2 I omega squared without the 1/2 mv squared. But in general, you're probably safest, if you're not sure, to use 1/2 mv of the center of mass squared plus 1/2 I around the center of mass omega squared. So let's take a look at a real quick example. Notice I've got a double pulley system. I have a 30-pound mass attached to this inner pulley, which has a radius of 1/2 foot, and a 20-pound mass attached to the outer pulley that has a radius of 1 foot. I'm being told that the omega is to the clockwise direction at 20 radians per second. And that kind of makes sense if you think about the moments that are involved. 20 pounds is pulling clockwise at a distance of 1 foot, so you might think of that as 20 foot-pounds. It isn't, but let's just think of it that way. And then 30 pounds is pulling in the other direction at 1/2 foot, so that's only 15 foot-pounds. But I should point out, it really doesn't matter what direction this is going. It could be going to the right and speeding up. It could be going to the left or counterclockwise and slowing down. And so be really careful about the direction. But remember, kinetic energies are I omega squared or mv squared. So the direction really doesn't matter because you're going to end up squaring it. So the pulley system has a weight of 50 pounds, that's mg. And the centroidal radius of gyration is 0.6 feet, so k sub g is equal to 0.6 feet. And I is going to then be 50 pounds over g, because remember it's mass times k squared, 0.6 feet quantity squared. And that's going to be the rotational inertia about the center of mass O. And since the fixed axis is at O, that works out very nicely. Cylinders A and B are attached, and what I'm interested in is the total kinetic energy. So the total kinetic energy here, there are 3 bodies. I could say sigma from I equals 1 to 3, because there are 3 bodies here. But I'm just going to write it out this way. It's going to be 1/2 the mass of A times the velocity of A squared plus 1/2 the mass of B times the velocity of B squared, right? Here's A, here's B, plus 1/2 I about the center of gravity omega squared. That's the kinetic energy of rotation for the pulley. Well, I know m sub A and m sub B, that's 20 pounds over g and 30 pounds over g respectively. I know omega is 20 radians per second. Now I can use that to figure out what the velocities of A and B are going to be. So at 20 radians per second, and this is 1 foot out, the velocity of A is down. Velocity is equal to r omega. So this is equal to 1 foot times 20 radians per second. And so my total velocity here is going to be 20 feet per second. And it's downward, but I really don't care because I square that. And so as I look at the velocity of B, the 20 radians per second is going to give me a velocity of 1/2 foot, that's r, times 20 radians per second, which is 10 feet per second, and that's up. And again, I don't really care about direction because I square that velocity. And so my total kinetic energy in this case is going to be 1/2 20 pounds over g, because that's going to turn it into a mass, times 20 feet per second, and I square all that, plus 1/2 30 pounds over g, times 10 feet per second, and I square that, plus 1/2 I, which is right here, times 20 radians per second, and I square all that. So this I is going to be 0.559, and my units pounds over gravity is slugs times feet squared. So I'm going to substitute that into the moment of inertia. And as I put all this together, I get 282.6, and that'll be pound-feet. Again, I've got slugs here times feet squared per second squared. That's going to give me pound-feet in all three cases. So there's the kinetic energy of that system.